All right, back again, and just looking at to see where things are here. It's about 7 million ticks or time units since the last video, and it's I looked at this thing here and there throughout the day, and it's changed. It's gone from a lot of different things throughout the day. It did look like one time during the day it was perfectly wavy. Um, like in the last time when you saw like a curvy line here, like four of them, going down, curve. I was trying to understand the reason for the curve versus straight down, but then when I thought about it, um, I realized that when you have straight up and down um, lines, um, they are separate lines. So you'd have four or five like parallel lines, mostly equal distant, but not always. Sometimes they'd have to shift a little bit, and they'd shift, and it'd be hard to tell for them. How to keep them precisely equal distant, and then to maximize the positions when like new organisms are randomly spawned on the map. So it's a little hard to manage because these guys can only see 5 units ahead of them. That's it. Um, and then when you see like the four curves, it is actually all one line actually, because that, remember I said that the top of one line, like when you go 1 unit above here, it brings it back here. So this is actually a whole line that extends. Um, and this thing here, the curve, once you go 1 unit up, this is a continuation down here. So I think the reason why it did that was because by having it all one like angled line, it'd be like this, and then another one would be like this. Uh, I was thinking it helps it have more control over making sure they're all properly distributed, and allows it to have more control over keeping the distribution between each band on this map. Uh, um, that's just a guess. And the way that it's not doing it so much anymore, but you see how you see just a lot of movement here. I'm wondering if that's because if you keep the whole thing moving, in the event that when an organism dies, becomes food, it's not just food for a single organism, whoever happens to be next to it. It lots of organisms could come by and take a nibble at it and keep moving or whatever. Um, and kind of like a circulatory system where it's you eat something and then all that nutrients get spread throughout the organism. So it's not just whoever happens to be right next to it gets the food. I don't have enough. I don't have any stats on that. I don't have anything going over here where I can track that. Like on average, how many units are eating a single unit of food? I don't know. Um, I did notice kind of a bug. It's not really a bug, but it was an unintended code on my part. When I click on any of these guys that are kind of not really doing anything, first letter of the output is the K, so that means it's sending the K command, um, and then this app is processing the K command. I was gonna put something as the K command, and I decided not to do it, so it doesn't do anything. All right, so here's the code where I'm processing every command, and see certain commands take certain amount of life. Um, like when they try to eat. If they try to eat and there's some food ahead of it, it takes away 50 from the food and gives you 50, unless the food's almost gone. Then it just takes whatever's left. But if you try to eat and there's no food in front of you, well, I'm gonna count that as an action that is gonna take 2 units of energy from you. So um, most most of these um, take energy. I like attacking. I have it take three. I have it take three away. If they send an attack command, there's another organism ahead. If there is an organism ahead, it's gonna take 75 away. Or if there's less than 75 in that life form, it'll take all of it away. Uh, for just moving, like moving forward, backwards, left or right, that takes two away. But yeah, it's like, and I have this one command called basically a rest. I called it S for sleep, but in the event that it just doesn't see that it, it determines that there's nothing to do or worth doing at that unit of time, just don't do anything. And there's a benefit to that. It only lose one energy. You can't do that forever because you're losing one energy every unit of time. You got to do something eventually, otherwise, just it won't make it. It'll just die eventually. But it is a way to conserve energy. Don't waste a lot. Um, I had some actions here. This is not relevant to the scenario I have on the map, but I have objects. Well, actually, I think you can push and pull food. I don't know if they're doing that. Um, you can basically have the option to push or pull. It moves um, the object, allows them to manipulate the location of an object by 1 unit. Um, and that takes 4 units of energy if the move operation is successful. Otherwise, it takes two. Um, so way at the end of all this, I got this else if stuff. Way at the end, I have some other command, just take away one, which that's the same thing as rest. So that's why, when they're using K like that, it's really the equivalent of rest. All of these are. Anything that says nothing on it, there's minimal cost then to the life form. These are all equally preferable to performing an action when cases where there's no action needed. So it's kind of just using the K command as a rest, because K command isn't actually doing anything. I was gonna use K command as like, so I have a limit on the Turing machine that it processes the input. If a Turing machine hits a loop, I mean, it could hit an infinite loop. Uh, and I can't. It's very easy to create an infinite loop too in a Turing machine. But on the other hand, it's possible that the thing could get complicated enough where maybe it needs to do 10,000 steps through a Turing machine to get to the output it's trying to get, and it's a good output. But so, but what I did to try to get around it, and there's no way to get around it. It's proven that it's called the halting problem. You can't figure out whether set of computations will hit an infinite loop or not. Uh, the Yeah, the way I'm dealing with that is I'm limiting the total steps to 10,000. In the event that it finishes, it does reach one of those double circled acceptance states. That's what they're called. Or if it crashes, basically it hits some input that it doesn't know what to do with, so it's considered like a crash, and it just returns nothing then. And in the event that the total steps is if it reaches 10,000, then it's considered okay. We're not going to do anything with that either. So I mean, what one thing I could do is start measuring like average number of um, average number of steps. Um, yeah, like yeah. I mean, the way I've seen these Turing machines designed right now, they have a ton of final states. Um, there aren't many cases where uh, it does need a lot of steps, so it doesn't require any deep computational effort. In case it's need to evaluate a bunch of variables, and it takes a long computation to figure it out. And um, yeah, that thing I put in with the 10,000, it is working right now. But if this thing were to ever advance, maybe I could have like a formula based on the number of states of the Turing machine, or use statistics to kind of get average number of steps for a typical Turing machine would need at that moment. Um, yeah, so but as of right now, I just capped it at um, 10,000, which is more than plenty at this point. Um, Freeze these guys for a second here. Yeah, so throughout the day when I looked at this, I saw it kind of revert to the parallel lines again for a little bit, and then it went to the multiple like multiple waves, even though it's all just one long line. And now it's doing this thing again. It was doing this earlier today too. And another thing I'm noticing is number of mutations is it's gone up quite a bit too. I mean, now that it did do this design the way it did do this like behavior change. There's a lot, considering all the movement now. There's a lot of potential to of things to improve. To perfect it. It's very chaotic at this point. So you see a lot more mutations because there's a lot of stuff that can be updated. I think like fixed and adjusted. And that's probably like what I'm kind of expecting. I guess from this, you might see something like where it does reach like a nice point where everything seems stable again, and then maybe something will happen where it'll change to something else again, change to another type of design, and then you'll see the mutation start ticking up again really quick to uh, help deal with all the problems that come up with the behavior change. I think the biggest hurdle for this whole thing is uh, basically just computational speed. Even if this kind of approach were used to create something like an artificial intelligence, that uh, uh, the hardest part is getting there with uh, computation speed. Running it from an app like this, it might be added. I mean, it might be possible to make an artificial intelligence just running it like this, but it might take forever. Not forever, but you know, decades or 100 years. I don't know. I don't know how long it would take. If it's possible, it might take a long time, but still possible. Um, and another concern was the environment. The initial conditions of the environment, controlling how many spawn. What's the grid size needed to be in order to advance it to a really intelligent level, or what's the mutation rate? What should the mutation rate be? Um, what's what kind of initial conditions would make this thing as most efficient to get to that highly intelligent level? 'Cause that's like a pipe dream. That's what I thought. I mean, it's like a pipe dream way up there. Like, oh, that'd be so cool if I could do that, where it just get like uh, just uh, a spiral of growth, intelligence, and uh, I mean, I think it was. I think this thing's capable of that. Uh, but finding that, finding it, and waiting for it, and what are the chances it's going to happen? You know, even if there is a chance, what's the chance, and how much computation speed is needed? Um, one of the ways I thought of like how to find the right environment is to like for a genetic algorithm to allow a genetic algorithm to advance something like this to uh, like an AI or strong AI, something that's like has sentience or something. You know, it's just something that's really useful. Maybe make a genetic algorithm that of different environments. So a genetic algorithm to find the right um, the right environment to um, so maybe run uh, like a few hundred of these at once and then plug a bunch of initial conditions, see which ones have the best luck at um, at growing. You know, the way we're trying to make them grow. And but again, the problem is computational speed. You don't have the computational speed for it. But the way around that is either if this thing were run on a supercomputer or a distributed computers, and it would not be that there's plenty in this thing that could be distributed to other machines to like if you run over a network of different machines that are all using like um, here. So the way I have it work is first off, as one optimization, the way I was going to do it originally was just have it cycle through every single square in the whole world, and if there's a life form there, evaluate it. But I figured that would take too long because going through every square, knowing that most of these squares are going to be blank, uh, you know, see how most of them are white. It's just was seemed pretty inefficient. I had a feeling that this was going to be like this. So what I do is I store the organisms in a list, and then I also have the grid point to them. And then when I need to evaluate the world, I just go through the whole the whole list of life forms, and then yeah, and then basically figure out their input and send it into them and get their output. Yeah, and then I put the output in the um, like a put the output in their uh, the output and save their output for when I actually process the output. Um, that was another issue I was wrestling with how to deal with um, how to deal with collisions in a two-dimensional world. Um, I'll show you what I mean. So, like, here, I'll stop these guys. So let's say you got this guy here. You got this guy here, and he's going to move left. Right, yeah. He's going to move left, and this guy is going to move right. Now, technically, when this guy moves, should this guy be allowed? I mean, if this guy's only allowed to move right when there's an empty square, and this one's only allowed to move left if there's an empty square there. Well, if this one decides to move right at the same moment, um, yeah, if this one decides to move right at the same moment this one is deciding to move left, then should that be allowed? Um, should they be allowed to basically swap places? I decided no on that one, I think, because it's kind of like counterintuitive to um, collision. Um, then there was, I was also wrestling with why even have collision? Why not just allow them to all be capable of occupying the same square? Then I don't have to worry about any of that. Having to check if something's there or not before you move in there. And I think what I'm doing is the squares are first come first serve. So if they're so if let's say one square is here. Let's see if I can grab an example I could show. This one's fine. So let's say this one wants to move down, right? And this one wants to move up. Well, they're both going to be processed at exactly the same time. At least it's kind of like simulated um, multiple parallel processing, even though it's only single processing. So you have to give it to one of them, right? Or you could say, oh, there's a collision and both try to get to the same spot. Therefore, no one. Since there's dispute about who's going to be in the square, we're just not going to let anyone move at all. That's the other way, I guess. But the way I do it is wherever you figure out all the places that they're intending to move. So I would first loop, I would say, okay, this one's going to go down, this one's going to go up. Okay, so you figured out what they want to do in the first loop. Second loop, you actually do what they're doing, what they want to do, and it's first come first serve. So let's say I end up processing first, and then they go down, and by the time I get to this guy, it's going to check. Okay, is there anyone there? Well, there is now. So you're not allowed to go up. So that's how that works. And I think I go through the list of life forms. So I guess the one who would get the advantage is I'm adding them to the list. And if I'm starting from the beginning of the list first, um, then I guess the oldest one gets precedence, and the older you are, the more likely you are to be given a disputed spot, which I guess that's fair. If you've been around longer, you should get priority. It doesn't matter. I mean, these are little things. I think either way, like any way you do it, it's still the same concept. So, but these little things trip me up. So it took me longer to code it than I would have liked. This is where the next loop where it decides how to. But yeah, anyway, that K command. Um, yeah, so the K command would have been still in there. I got the placeholder for it, but this is what I was going to use it for. So let's say it's kind of like a compromise for the loop issue where I um, I allow for well, I only allow 10,000 steps for a unit of time. I was going to use this as like a workaround in case they really needed to be able to evaluate their situation longer than 10,000. They could sacrifice another unit of time, and what it would do is it would keep the processing of the previous time where it is, um, and just keep evaluating it, trying to figure out kind of like when like we need sometimes we need more than one unit at a time to think about something or do something. So we don't that's not how we work either. Sometimes we need more than just a little bit of time to make a decision about something. So I thought if you really need it, well then here you go, you got it. Um, you can use this K command if it finds it useful somehow. But luckily, I'm not running into that problem at all. It's only a couple. They're only using a few steps in the Turing machine, so it's not a problem. This was another option I retired to, giving them the choice to whether they want to procreate or not. Because I figured, at first I was gonna just give them the choice, procreate whenever you feel it's appropriate. Um, 'Cause I thought that is automatically going to naturally be used, because if they don't procreate, then anything that doesn't procreate just dies. So if there's anything that's going to persist, it's going to be stuff that chooses to use the P command. It's one of those natural things where um, I just want to give them a choice. But then I thought, well, life forms, I don't think they choose when to procreate. Uh, it just happens. Unless, it's abortion or whatever, or whatever, the stuff that they can choose to do, not do the stuff that would lead uh, to not to lead to procreating. And if that's the case, I mean, I do have that ability in there too. I mean, you can still eat food, just don't eat all the food, and then uh, it won't spread its genetics. Yeah, but anyway, I think the way around the problem of the slow growth. I mean, if I had tons of computing power, this wouldn't be as big a problem to deal with as far as the slowness of the. I mean, if you run this thing for days and you only get like 602 modifications to the original, uh, that's running this thing for days, and that's. But if you could imagine this thing being run on 1,000 computers, this I'd be where I'm at right now, and probably a few seconds or a few minutes or something. Um, and then I could really see a lot of progress then. So it's really the computation speed that's holding this thing back. Uh, there was like take out parts that can take out a lot of the work that can be spread out among multiple machines. Since each machine is evaluated, um, each machine is evaluated uh, on its individually. You could let's say you had like a bigger world with uh, uh, like a million machines. You could pass those machines down to other computers on the network. It has to be a big enough workload where any like network time to communicate like network traffic. Um, uh, when it would be faster than any lag time from communicating over a network, transmitting the processing. Or maybe you could have like this, something like this. Like everyone has their own grid. Um, everyone has their own grid that they're in charge of, and they're just running it like the way I'm running it, but they're all interconnected. And no, that won't work either because you got to synchronize the time among all of them. Yeah. Anyway, yeah, a parallel. I think that would be the approach because I'm limited here. I don't have enough um, processing speed just by the nature of genetic algorithm. It's slow, but it will get there, but it's slow, and but I think it would be faster if I had competitive. If I set up a competitive scenario where I think that's the trick to make it more interesting than this. This they're all working together right away. Uh, I think it's going to be the competition that a competitive behavior uh, that really you would see something like intelligence spawn from. All right.